These are the frequently asked questions for Algebra 2, Section 9-1, Day 2. And I'm going to start here with some of the problems that are just typically the toughest for students that are new to sequences and series. And that is writing an explicit formula for each sequence. So in number 25, what I want to do is make my chart. Take a look and see if there's anything that just pops out. As I go through this. Now, what we have to do is remember that these are explicit formulas, which means we don't take a look at the previous terms. What we need to do is think, how could I use n to generate this number? So you need to have a relationship directly between 1 and 4, 2 and 7, 3 and 10, 4 and 13, 5 and 16. And again, we do always hope that we could look up there right away and say, oh, 1 plus 3 is 4, so they're adding 3. But 2 plus 3 is not 7, so that isn't going to work. Now I do notice that these numbers are going up. So what I would try is I would try some multiplication and say, all right, well, let's try 2 times n. So what I have to do is make a formula that uses 2 times n, where I could input, I'll just put a little I there for input of 1, and get an output of 4. Well, if I put the 1 into 2n, I'm going to get 2. And that's not 4, so I'd have to add another 2 to make that work. Now if I put a 1 into this formula, I will get 4. But the question is, does that work for the next value of n? So what I have to do is try it with n equals 2 and see whether or not it works. Well, 2 times 2 is 4, and 4 plus 2 is 6. It is not 7, so that is not the right formula. So I'm going to go back and try 3 times n. So now, again, if I put an input of 1 in, I have to get 4. So if I put a 1 into this, it'll be 3 times 1 is 3, and I would need to add 1 to get a 4. So now my hope is that this will work, because this formula didn't. So now if I go to the second term, that will give me 3 times 2 is 6, and 6 plus 1 is 7. So far, so good. Now I would try the third term. 3 times 3 is 9, and 9 plus 1 is 10. Again, keep trying just to make sure. 3 times 4 is 12, 12 plus 1 is 13. 3 times 5 is 15, 15 plus 1 is 16. Fantastic, found it. So to find any term, what you need to do is take 3 times the number of the term, and then you need to add 1. And it is just a methodical search. By looking at the numbers, they were going up. I tried addition, that's the most basic thing that we can try. It didn't work, so then I tried different numbers for multiplication. And then with this group of problems, they also want us to find the 10th term. So once I have my rule, now I need to find the 10th term. And that's really easy once you have your rule. We can see 3 times 10 is 30, and 30 plus 1 is 31. So there is the 10th term. That's why it's so important to get that rule correct before you begin. Now, I'm going to have to erase this. And going to number 27. All right, so 27 looks very interesting. So let's take a look at what we have. I have n equals 1, 2, 3, 4. And whenever a sequence comes with mixed numbers, I often think, you know what, they're trying to hide something from me. Because we don't use mixed numbers a whole lot when we're doing calculations in mathematics. Usually we'll use improper fractions. So the first thing I would do is transfer these mixed numbers into improper fractions, just convert those. So negative 2.5 would be a negative 5 halves. Negative 2 would be a negative 4 halves. Negative 1.5 would be a negative 3 halves. And a negative 1 we could write as a negative 2 halves. Now, why did I do that? Because it's incredibly obvious that the bottom part of our fraction for our answer needs to be dividing by 2. We're always looking for something that these things have in common. So my rule so far is that I need something divided by 2. Now that I've taken care of those 2's, I don't even look at those anymore. That's a part of my formula, it's done. What I need to do is figure out, is there something basic you can do to a 1 to get -5, 2 to get -4, 3 to get -3, and 4 to get -2. And I realized that's subtracting 6. If I take 1 minus 6, I will get -5. If I take 2 minus 6, I will get -4. If I take 3 minus 6, I will get -3. And if I take 4 minus 6, I will get -2. This is my explicit formula. Formulas often, I know we don't tend to like fractions, but when you have sequences and series, fractions many times are much easier to write than just a list of whole numbers or integers. Now again, I'm supposed to find the 10th term, so that means I need to take 10 minus 6 and divide it by 2, and that of course is 4 divided by 2, which is 2. So my 10th term would be a 2, and that one, again, you change those mixed numbers into improper fractions and things will start to happen for you. Number 29, we'll get that one up here. So making that table, writing down those terms. All right, so I'm writing these numbers down. And again, if we can't see it right away, that means we need to actually just go through it and say, is there something easy I can do to 1 to get 2, 2 to get 5, 3 to get 10, 4 to get 17, and 5 to get 26. It's not addition. We're not adding the same thing every time. Then you would try multiplication and see if that works. Now, when you get to trying 2 times the number, remember it's an input of 1 that needs an output of 2. So you put the 1 in, and 2 times 1 is 2 already, so then you'd have to add 0. And you look at the next one and you realize, well, absolutely that's not going to work because 2 times 2 is not going to give me 5. But while you're doing that 2 times, hopefully you start thinking, wait a minute, if it's not going to be multiplication right away, because I could try 3 times, 4 times, and 5 times, and it's not going to work with this one, maybe it's squaring instead. So 1 squared would be 1, and I'd have to add 1 to get the 2. 2 squared would be 4, and I'd have to add 1 to get the 5. 3 squared would be 9, I would add 1 to get 10. 4 squared would be 16, I'd add 1. 5 squared, 25, add 1. Now, that one, while I was writing down the 2, 5, 10, 17, and 26, I was thinking to myself, wait a minute, these are 1 away from the perfect squares. And that's kind of the thought process that you need to have when you're looking for sequences and series and you can't find them. You need to think, wait a minute, these numbers are close to something that I know those perfect squares. And then oftentimes it'll go a lot faster. So if I need the 10th term, I need to take 10 and square it, and then add 1. And that's going to be 101. So here is my rule, and there is my 10th term. Next one is number 31, and I will get that one up there so that we can take a look at that. With this one, we have a first term of 1, then 3, then 9, then 27. Now as you're writing those down, I hope you're thinking, wait a minute, that's getting multiplied by 3 every time. Well, constantly multiplying something by 3 every time is also powers. So what we want to do is think, okay, well, maybe it's 3 times something, and give that a try, and if that doesn't work, then we'll think powers. So we've got this 3 that we know is involved here. So 3 times 1 would be 3, and I would have to subtract 2 in order to get the 1. So now I try putting a 2 into that, and that'll give me 6 minus 2, which is 4. And I realize that's not it. So I notice that pattern of 3, and I think, well, this is 3 to the first, this is 3 to the second, and this is 3 to the third. Wait a minute, that's 3 to the 0. So my rule will be 3 to the something. I have to figure out how to get that power, and that power comes from, what do you do to 1 to get 0, 2 to get 1, 3 to get 2, and 4 to get 3, because when we are using explicit formulas, we must use n to write these. And what you do with each one of those is you subtract 1. So 1 minus 1 gives you 0, 2 minus 1 gives you 1, etc. 10th term. So we need 3 to the 9th. Probably grab a calculator for that one. I don't know many people that would have that memorized. So the 10th term would be 19,683. So again, while you're writing them down, don't just be blindly writing them down. Be thinking about, how do I know these numbers? You know, where have I seen these numbers before? Or these are really close to some nice numbers that I've worked with before. And that's what you want to do. All right, then the next ones, we'll just find the 8th term of each sequence. So we wouldn't have to write a rule for these. We would just have to notice the pattern and go from there. So number 39, we take a look and notice it goes from 2 to 1 to -2 to -7 to -14. So the thought would be, maybe it's just subtraction. So let's check that. 2 minus 1. 2 minus 1 would give you 1. And then 1 minus 3 would give you -2. -2 minus 7, that's going to get you a difference of -5, and then -7. And we can see what they're doing is they are subtracting the odds there. So the next thing that we would do is we would take, if we want the 8th term, we already have the 1st, 2nd, 3rd, 4th, and 5th. We could just keep doing this recursively since we only need a few more. So we would take -14, and we would subtract, sorry, doing a lot of yawning here, I'm really tired. We would subtract 9, and that would give us -23. And then we would subtract 11, and that would give us -34. And then we would subtract 13, and that would get us -47. 5th term, 6th, 7th, 8th. So the 8th term is -47, because again, it didn't say we had to write a rule, so we don't have to write a rule with these. We just have to be able to find that term. Number 41. This is another one where it's kind of interesting because one of them they did not write as a fraction, and all the other ones they did. So I want to look for that pattern, and I see, well, 2 is really 2 over 1. Just giving you a second here so that you can take a peek and see, wait a minute, that goes there. And then they continue to go up each time. So that's the pattern, along with the fact that every other one of these is negative. So let's see. If the 4 came down on the bottom here, well, that must mean that the 5 is going to go down to the bottom on the next one. And then we need to put the next highest number in the numerator. 2, 3, 4, 5. So a couple of different ways to look at this. The first way you could look is, hey, they're always going down to the bottom. Or you can separate the numerator and the denominator, and you'll notice this is 2, 3, 4, 5, 6, 7, 8, 9, etc. And then on the bottom, 1, 2, 3, 4, 5, 6, 7, 8. And then every other one of these needed to be negative. So we had 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th term. So lots of different ways to notice sequences and how they've been generated. As long as you can get the one that you need, that's what's going to be important. All right, next, I have a lovely word problem. Oh, actually, I had a couple more here I was going to do. All right, so let's talk about 44. Determine whether each formula is explicit or recursive. Okay, so this hinges on the fact that when we talked about these, I kept telling you recursive has to refer to the previous term. So as I look at these, 43 is going to be recursive because it has that symbolism for the previous term. 46 is going to be, 46 was recursive there, and then 47 and 48, nope, no recursive stuff there at all. So we'll talk about 44. Determine whether it's explicit or recursive. 44 was explicit. We did not see any use of the previous term in there. And then it says find the first 5 terms of each sequence. So for the first term, we're going to have 1/2 times 1 times 1 minus 1. So what we have to do is remember the order of operations and go ahead and do parentheses first. This is going to give us 0, so the whole thing is going to be 0. So when you multiply by 0, we're going to get 0. And then we have 1/2 times 2 times 2 minus 1. So that will be 1/2 times 2 times 1. Well, that's going to give us 1. Third term, 1/2 times 3 times 3 minus 1. Well, 3 minus 1 is 2, and I'm going to go ahead and change the order here and say, all right, 2 times 1/2 is 1, 1 times 3 is 3. Move this a little bit. All right. Fourth term, 1/2 times 4 times 4 minus 1. So with this one, I'm just going to go straight across here. 1/2 times 4 is 2. 4 minus 1 is 3. So that will give us 6. And then the fifth term, 1/2 of 5 times 5 minus 1. Well, 5 minus 1 is 4. 1/2 of 4 is 2. And 2 times 5 is 10. So there are the first 5 terms of that sequence, just using the formulas there. All right, 46, recursive, because it has the notation for the previous term, and then we know the first term is -2, so that's a freebie. So to find the second term, we read off this formula, and it says, to find any term, take -3 times the previous term. Well, my previous term was -2, so -2 times -3 will give me 6. And now all I have to do is keep multiplying by -3. While I'm yawning there, I'll do a little math out in front of you. And then we have 54 times 3. So -162. So again, we just generate them, and recursively, you can get those several terms in a row pretty easily. All right. Now number 50 says use the given rule to write the 4th, 5th, 6th, and 7th terms of each sequence. So they're just making sure that we remember how to write these. So 4th, 5th, and 6th, this is an explicit rule, so to find the 4th term we need 2 times the quantity 4 minus 1 cubed. So that will give us 2 times 3 cubed, which is 27, and that will be 54. 5th term, 2 times 5 minus 1 cubed, well, that's going to be 2, and 4 cubed is 64, so 128. 6th term, 2 times 6 minus 1 cubed, and that's going to be 2 times 5 cubed, and 5 cubed is 125, so that is 250. 7th term, 2 times 7 minus 1 cubed, so 2 times 6 cubed, which is 216. And we'll multiply by 2 and we get 432. So 54, 128, 250, and 432. Just generating those next terms. Yeah, you can do 52 on your own. You just need to put your n values in there and then just work slowly and carefully. Okay, here's the word problem. Get that back out of the way. Think about a plan. I thought this was earlier in the assignment. You invested money in a company and each month you receive a payment for your investment. Over the first 4 months you receive $50, $52, $56, and $62. If this pattern continues, how much do you receive in the 10th month? And it says, what pattern do you see between consecutive terms? And then can you write a recursive or explicit rule to describe the pattern? And how can you use your formula to find the amount you receive in the 10th month? So, a couple of ways to think of it. We've got 50, 52, 56, 62. And those were your first 4 months. So months 1, 2, 3, and 4. Kind of thinking of this as a table. And we notice here that the first month we're adding $2. Then $4, then $6. And recursively, we're going to the 10th one, so it wouldn't be really awful to just say, okay, I'm going to add 8, then I'm going to add 10, then I'm going to add 12, and go about it that way. And that's because the explicit rule for this one is not very pleasant. So what you would probably want to do is say, all right, 62 plus 8 is 70. Add 10, 80. Add 12, 92. Add 14, 106. And I'm going to write that 106 down here again. Add 16, 122. Add 18, 140, add 20, 160, and let's see what month I'm in now. If this pattern continues, how much do you receive in the 10th month? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A little past it. $140. Now, like I said, with this one, that truly is the easiest way to do this. I'm going to show you what the explicit rule is for this, but it is not fun. And that is, to find any month that we need here, you would take 50 plus, and then the formula ends up being n times n minus 1. And that takes some doing to figure out what's going on there. And the reason it's 50 plus n times n minus 1 is instead of thinking, hey, this is 50, 52, 56, and 62, you'd say, all right, so I'm starting off with the 50, and then it's an increase of 2. Then it's an increase of 6. Then it's an increase of 12. And you would use that pattern in a table to figure out how you get this to work. And once you have that in a table, and actually I should at least put down the 4 so you can verify it with a couple of these. So you can see, you'd realize, hey, if I take 2 times 1, I get 2. If I take 3 times 2, I get 6. If I take 4 times 3, I get 12. 5 times 4, I get 20. So that's the reason that that formula works the way that it does. You're taking the number of the term times the number of the term that was right before it. So 2 times 1. Like I said, easiest way with that one would just be recursive and go with it. All right, number 55, find the next 2 terms in each sequence, write a formula for the nth term, identify each formula as explicit or recursive. So this is where you get to pick, So you look at 55 and find the next 2 numbers in each sequence. We hope it's something easy. It is going up. So we check addition, and sure enough, they are just adding 3 each time. So the next number would be 20, and that would be the 1, 2, 3, 4, 5, 6th term. And then the 7th term, 23. Now, because it was really easy to see that they're adding 3 each time, you probably want to write this one recursively and say, all right, to find any term, take that previous term and add 3. So this one, very quick and easy recursively. We don't need any of the larger numbered terms, so we can go ahead and write that recursively. 57. We have 1, 8, 27, 64, and 125. And hopefully right now you're thinking, wait a minute, aren't those the perfect cubes? Because that'll make this go really fast if you identify those. So we have 5 to the 3rd up there. That would mean 1, 2, 3, 4, 5. We need the 6th term to be 6 cubed, which was 216. We just used that on an example a minute ago. And then we need 7 cubed, which is going to be 343. Now, in order to get that, very easy. You put the table up there and you realize, oh, for goodness sake, all we're doing is take an n and cube it. So a sub n equals n cubed. And that is an explicit rule because that uses the number of the term to generate the term. And that is, of course, best case scenario. That is really what we would like to do every time, if we can. But sometimes it is easier to write recursive. All right, 59, hopefully you're looking at that and saying the same thing, except, hey, those are perfect squares. So how do I get those, you know? Well, first of all, we'd say we've got 5 terms up there. We need the 6th one, which would be 12 squared. And then we need the 7th term, which would be 13 squared. But what we would want to do is go ahead and put those numbers up there and say, okay, what could I do to 1 to get it to be a 7? Because then I could square it. Well, you'd have to add 6. What can you get 2 to do to 2 to get it to be an 8 so that I could square it? You'd add 6. And you see that this works all the way down the line. So what we need to do is take the number of the term and we need to add 6 to it, and then we need to square it. And that will be an explicit rule, remembering that, you know, explicit, if we can write every rule explicitly, that's what we want to do. And that was a nice pattern that could be found pretty easily. So that's the way I'm going to write that one. All right, what's left? Oh, from the next section here, just a couple of these. Determine whether each sequence is arithmetic. If so, identify the common difference. Remember, in order to be arithmetic, they have to be adding the same thing every time. So I'm looking at these numbers thinking they're adding 10, they're adding 10, they're adding 10. So 7 is a yes, it is arithmetic. And the common difference is 10 because that's what they're adding every time. So for number 8, 1 plus 0 is 1, but 1 plus 0 is not 2. That's a no. It has to be the same number every time. And remember, it's called the common difference because to get it, you can work backwards and say 8 minus 5 is 3. 5 minus 3 is 2. 3 minus 2 is 1. 2 minus 1 is 1. And 1 minus 1 is 0. This does not come out to be the same thing every time. So that is not a common difference. And that is not arithmetic. That should do it for this section.